Picture a structure so immense and so perfectly aligned that it has stood for over 4,500 years. Its stones are cut with a precision that challenges modern tools, and its form is a testament to a seemingly impossible feat of engineering. Now imagine that this timeless marvel, one of the pyramids of Giza, was built without a single blueprint, not one detailed drawing, no stack of plans, no digital model. This is not a thought experiment, it is historical fact. The world's first engineers, the architects of our most enduring monuments, operated in a world without the paper plans we consider essential today. And the most remarkable part, they may have built better for it. This is a story that turns our modern understanding of design and construction completely on its head. We live in an age defined by meticulous planning, where complex software and detailed schematics are the foundation of every major project. We trust the abstract diagram, the two-dimensional representation, to guide us in creating a three-dimensional reality. But what if this reliance on plans has caused us to lose something vital? What if the ancient method, a profound, hands-on conversation between the builder, the material, and the site held a deeper, more resilient kind of intelligence? This is the provocative idea we will explore together. We are about to journey back to a time when engineering was not a science of paper, but an art of the senses. It was rooted in embodied knowledge, a wisdom passed directly from master to apprentice through years of shared labor. It was driven by a deep, tactile connection to stone and wood, an intuitive feel for balance and stress that lived in the muscles and the mind. This approach was not a primitive precursor to our modern methods. It was a sophisticated system in its own right, one that produced structures of a quality and longevity that we still struggle to explain. This exploration is more than a history lesson. It is an invitation to question the very foundations of how we create. We will uncover how intuition, apprenticeship, and a respectful dialogue with natural materials created legacies that continue to baffle and inspire us. We will challenge our unquestioned reliance on abstract diagrams and consider the possibility that the greatest blueprints were never drawn, but were instead held in the collective memory, the skilled hands, and the observant eyes of the builders themselves. Prepare to see the past and perhaps the future in a new light as we unlock the mysteries of history's greatest builders and discover the profound secrets they left behind, not in ink but in stone. Think of knowledge not as something written in a book but as a living flame passed carefully from one torch to the next. This was the reality for ancient engineers. In a world without paper archives or digital files, the most vital technical knowledge, the secrets of how to build structures that would last for ages, existed solely in the minds and muscles of skilled masters. This system of oral tradition and apprenticeship wasn't just a way to teach. It was the very engine of innovation and quality control. An aspiring builder didn't learn from a textbook. They learned by standing shoulder to shoulder with a master, year after year, absorbing lessons that could never be fully captured in words. The transfer of knowledge was a deeply immersive, almost sacred process. An apprentice would begin with the most mundane tasks, not as punishment, but as the essential first step in building a relationship with the materials. They would mix mortar, feeling how the consistency changed with the humidity of the air. They would haul stones, learning to judge their weight and density by the strain in their own backs. This wasn't busy work, it was the foundation of a physical vocabulary. The master would demonstrate how to strike a chisel, and the apprentice would mimic the motion, not just copying the angle of the wrist, but internalizing the rhythm, the sound of a good strike, and the subtle vibration that traveled up the handle. The correction was immediate and tactile. A master might place a hand over the apprentices to adjust their grip, or simply grunt at a poorly set stone. The knowledge gained was visceral. It was the memory of how a specific type of granite sounded when tapped with a hammer, a clear ring indicating solidity, a dull thud hinting at a hidden flaw. It was the learned intuition for when a wooden beam was seasoned properly, or the exact moment when a clay mixture had the perfect plasticity for brickmaking. This was embodied knowledge, a wisdom that resided as much in the sinews and the senses as it did in the brain. A modern blueprint can tell you the dimensions of a dovetail joint, but it cannot teach you the feeling of the wood starting to resist just before the fit is perfect, a sensation that tells the carpenter to ease up. This deep, physical understanding created an unbreakable chain of quality. The nuances of the craft, the little tricks for handling a tricky material, the warning signs of structural stress that appear long before a crack forms, were passed down with a fidelity that a static drawing could never hope to achieve. This method built incredible resilience into the entire engineering process. If a master fell ill or passed away, the knowledge wasn't lost in a locked filing cabinet. It lived on in a dozen skilled apprentices, each carrying a part of the whole. The community itself became the library. This intimate, human-scaled system of learning was the ancient world's true blueprint, and it provided a critical advantage that our modern, abstract methods often struggle to replicate. This deep, embodied knowledge was only half the story. The other half unfolded in a silent, continuous conversation between the builder's body and the material world. We tend to picture an ancient architect deep in thought, perhaps sketching in the sand, but the reality was far more dynamic. These engineers thought with their entire physical being. Their primary design tool wasn't a stylus or a chalk line. It was a profound, innate sense we can call kinesthetic intelligence. This is the body's own genius, the ability to understand weight, balance, tension, and spatial relationships through movement and touch. For a master mason shaping a granite block for a Roman aqueduct, a two-dimensional cross-section drawing would have been almost meaningless. His real blueprint was the feeling in his hands and arms as he worked. He would hoist a block into a near-fit position and then begin a delicate dance. With a slight push, a gentle rock, he would listen not with his ears but with his nerves. He was feeling for the subtlest vibration, the faintest whisper of a wobble that indicated an imperfect contact point. His hands became sensitive gauges, measuring friction and weight distribution directly. This real-time, tactile feedback loop was instantaneous. The stone itself would tell him where to chip away next, guiding his tools with a precision that no abstract measurement could match. It was a physical dialogue where the material was an active participant in its own shaping. This process allowed for micro-adjustments so fine they are invisible to the eye but crucial for structural integrity. A plan might call for a perfectly flat surface, but the mason, through this bodily conversation, might instinctively create a surface with an almost imperceptible curve or a slightly textured finish that actually created a stronger bond with the mortar, a solution born from feel, not from theory. The body became a living, breathing calculator, sensing complex physics in a way that transcends numbers. A carpenter fitting a complex joint would feel the increasing resistance as the wood slid into place, a pressure that communicated the tightness of the fit far more accurately than any caliper. This kinesthetic sense could detect harmonic resonance the way a well-built arch seems to sing with stability, or the dead feeling of a structure under hidden stress. This wisdom led to solutions that felt right because they were inherently stable and organic, emerging from a direct response to physical laws rather than an attempt to impose an abstract idea upon them. This bodily intelligence granted a fluidity and adaptability that a rigid, pre-drawn plan simply cannot accommodate. If a stone split in an unexpected way during carving, the mason didn't need to consult an authority or wait for a revised drawing. His hands and eyes would immediately assess the new form and adapt the design on the spot, seeing new possibilities in the accident. This flexibility, this capacity for creative problem solving in the moment, was the direct result of thinking through the body, a language of construction that we have largely forgotten in our world of screens and specifications. But this conversation between the builder and their materials went far deeper than simple selection. Ancient engineers saw stone, wood, and earth not as inert substances to be dominated, but as living partners in the creative process. They understood that each material had its own voice, its own personality, and its own secrets to share if one knew how to listen. A master builder approaching a quarry didn't just see a source of blocks, they saw a library of potential. They would walk among the exposed rock faces, running their hands over the stone, feeling its texture, and observing the direction of its grain, what geologists call its cleavage. They were reading the stone's history, understanding how it was formed over millennia, and from that, predicting how it would behave under a chisel and under the immense weight of a structure. A skilled ear could learn even more. By tapping a potential block with a hammer, the builder would listen intently to the sound it produced. A clear, high-pitched ring indicated a dense, solid piece of stone with high internal integrity, perfect for a load-bearing cornerstone. A dull, flat thud, however, might betray hidden fissures or weaknesses, a flaw that could lead to catastrophic failure centuries later. But here's the genius: rather than discarding this flawed stone, they often found a brilliant use for it. A stone with a natural fissure might be intentionally split along that line to create two perfectly flat faces, saving immense labor. A softer, more porous stone might be designated for an interior wall where its weakness didn't matter, but its lighter weight was an advantage. They turned the material's so-called imperfections into structural features. This deep listening extended to wood as well. A carpenter knew that a tree cut in winter, when the sap was down, would produce a harder, more stable timber less prone to warping. They understood the different strengths of heartwood and sapwood, and how the natural curves and knots within a piece of timber could be oriented to actually increase its strength, much like the grain in a piece of carbon fiber. They worked with the wood's natural tendencies, not against them. And when it came to earth, the foundation of everything, this dialogue was perhaps most profound. Builders learned the unique settling patterns of local soils, how clay expands when wet and contracts when dry, how sandy soil drains quickly but can shift. They didn't just dig a hole and pour a foundation, they adapted to the land. They might design a structure with a wider base on a softer soil or incorporate clever drainage channels to manage water flow, ensuring the earth itself became a stable, supportive partner. This fundamental respect for materiality meant that every structure was a co-creation with the environment. The design was not a rigid idea imposed upon a site, it was an idea that emerged from the site. It evolved organically from the inherent strengths and limitations of the available materials. A building in a forest-rich area would naturally develop a timber frame aesthetic, while a civilization in a mountainous region would become masters of stone. This responsive adaptation resulted in structures that felt intrinsically rooted in their location. They were more resilient because they were designed from the inside out, working with the physical laws of their materials, rather than forcing those materials to comply with an abstract external ideal. This stands in stark contrast to much of modern construction, where materials are often specified from a catalogue to fit a plan, shipped across the globe, and then assembled with little regard for their local context or unique character. The ancient approach was one of harmony, a patient, attentive collaboration between human intention and the enduring wisdom of the natural world. Now, take this idea of a direct, hands-on dialogue and scale it up to the level of a cathedral or a pyramid. How do you manage a project of such immense complexity without a master plan locked away in an architect's study? The answer is as brilliant as it is simple. The construction site itself became the blueprint. The rising walls, the growing arches, the partially completed structure, this was not merely a project under construction. It was a full-scale, three-dimensional model that the builders could walk around, touch, and learn from in real time. Imagine a master builder standing before a newly erected section of a nave. He isn't just looking at a drawing. He is observing the actual structure, UNDER, Chinese letter loads. He can see how the morning light falls across the stones, revealing subtle shadows that hint at slight settlements. He can run a hand along a joint, feeling for any movement after a season of rain and wind. This direct sensory feedback was invaluable. If a wall began to show the faintest hint of bowing under the weight of a new roof, the builders didn't need to convene a meeting, revise a parchment drawing, and issue a change order. They could respond immediately, organically adding a buttress right where it was needed, its size and shape determined by the visible stress it had to counteract. The design was not a fixed script to be followed slavishly. It was an emergent property, a living thing that grew and adapted based on its own condition. Think of it like a gardener tending a vine, guiding its growth rather than forcing it into a rigid trellis. Each stone laid was a decision informed by all the stones that came before it. The building literally informed its own completion. This iterative process, this constant conversation between the builders and the thing they were building, ensured a profound level of structural honesty. There was no hiding behind a beautiful drawing. The physics of the situation were laid bare for all to see and feel. A design flaw would announce itself early, when it was still small and correctable, rather than remaining hidden on a piece of papyrus only to manifest as a catastrophic collapse years later. This method created structures that were perfectly integrated with their own reality, because the design evolved from that very reality. We have largely lost this dynamic of a living blueprint, replacing it with the illusion of total pre-control. But in doing so, we may have sacrificed the resilient, adaptive intelligence that allowed these ancient wonders to stand for millennia. So, with this deep, responsive dialogue between builder and material as our foundation, we come to a masterstroke of ancient organizational genius, the power of modularity. When you cannot rely on thousands of individual drawings to guide a massive workforce, you must find a way to embed the instructions into the very components being used. This is where ancient engineering reveals a breathtaking elegance. Instead of complexity, they embraced a profound simplicity. The Romans were the undisputed masters of this approach. They industrialized construction through standardization, creating a system so effective it powered the expansion of an empire. Think of a Roman brick. It wasn't just a piece of baked clay. It was a standardized unit of measurement designed to fit perfectly in a man's hand for easy laying, and more importantly, to fit perfectly with every other brick of its type. Similarly, the wedge-shaped stones for arches, called voussoirs, were produced in a limited set of standard sizes and angles. This transformed the immensely complex task of building a multi-story amphitheater into something resembling an assembly process. A master architect didn't need to provide a unique drawing for every single arch in the Colosseum. He simply established the fundamental proportional rules. He might decree that the height of an arch should be twice its width, and that all voussoirs for a certain class of arch would be cut to a specific template. With just a handful of these standard module types and a simple set of relational rules, the entire complex geometry of the building could be communicated to every team on site, from the quarrymen to the bricklayers. This created what we might today call a kit of parts. A worker high on the scaffolding didn't need to understand the grand architectural vision or interpret a complex plan. He simply needed to know that when he received a stone marked as a Type 3 voussoir, it went into the next available slot in an arch being built to rule set A. The intelligence was no longer concentrated solely in the mind of the architect or in a fragile set of drawings. It was distributed, baked directly into the standardized components. This decentralization was a key to its robustness. If one team fell behind, another could pick up the work using the same kit of parts without any loss of continuity. If a stone was damaged, it could be replaced with an identical one from the stockpile. No need for a custom replacement or a work stoppage. This system drastically reduced the opportunity for error and accelerated construction to an incredible degree. But its brilliance wasn't just functional, it was also aesthetic. The repetition of these standardized modules created a powerful, rhythmic beauty in structures like the Colosseum or the aqueducts. The endless rows of identical arches are not monotonous. They are a visual testament to the power of a simple, scalable system. The result was an architecture that was both massively ambitious and elegantly simple, demonstrating that true sophistication often lies not in adding complexity, but in finding the most intelligent form of simplicity. Yet, for all the brilliance of modular systems and physical intuition, there was a dimension to ancient engineering that reached far beyond the purely practical. To see these structures only as feats of construction is to miss half of their story. For the people who built them, engineering was inseparable from cosmology. It was a sacred act, a way of bringing the order of the heavens down to earth. The precise orientation of the Great Pyramid to the cardinal directions, accurate to within a fraction of a degree, wasn't just a technical display. It was a profound statement of alignment with the cosmos, achieved not with magnetic compasses which didn't exist but through patient, generations-long observation of the stars. The builders were not just aligning stone, they were aligning their kingdom with the eternal, unchanging cycles of the universe. This symbolic intent provided something a parchment blueprint never could, a powerful, unifying vision for every single person involved in the project. A laborer hauling a block under the scorching sun wasn't just performing back-breaking work, he was participating in a ritual that connected his community to the divine. This shared mental blueprint, this understanding that they were building a gateway to the gods or a vessel for a pharaoh's celestial journey, instilled a level of care and commitment that transcends modern notions of quality control. The drive for perfection became a spiritual imperative. A slight misalignment wasn't just a technical error, it was a cosmic imbalance, an offense to the gods that could bring misfortune to the entire community. This infused the work with a profound sense of responsibility. Consider the builders of Stonehenge hauling massive bluestones over hundreds of kilometers. The sheer effort involved is almost unimaginable. A purely utilitarian explanation struggles to account for such a monumental undertaking. But when you understand that these stones were likely believed to hold sacred healing properties or to be essential for rituals that ensured the sun would return after the winter solstice, the motivation becomes clear. The project was an act of collective survival and devotion. The process of building was as important as the final structure. Rituals would have accompanied every stage, from the blessing of the quarry site to the final placement of the capstone. These weren't superfluous ceremonies, they were the psychological and social glue that bound the community together in a common, transcendent purpose. The master builder was not just an engineer, he was a priest astronomer, interpreting celestial patterns and translating them into terrestrial form. The building itself became a vast astronomical instrument and a temple, its shadows and alignments marking the seasons, predicting solstices, and connecting the rhythms of human life to the grand dance of the cosmos. This fusion of practical need and spiritual meaning created a powerful feedback loop. The desire for cosmic harmony demanded extreme precision, which in turn drove innovations in engineering. And the successful creation of a structure that so perfectly captured this harmony would have reinforced the spiritual beliefs of the people, validating their entire worldview. The stone circle or the pyramid was not merely a building, it was a testament to a universe that was ordered, meaningful, and intimately connected to human endeavor. This depth of purpose, this fusion of the earthly and the celestial, is a dimension of building that our modern, secular approach often overlooks, yet it may be one of the most powerful reasons why these ancient wonders continue to captivate and endure. All this talk of building without blueprints might lead you to imagine a world with no planning at all, a kind of organized chaos, but it's crucial to understand what the actual alternative was. When we romanticize the idea of ditching plans, we're comparing it to our modern, hyper-accurate computer-aided designs. The reality for ancient civilizations was far more rudimentary. The alternative to no blueprints wasn't a perfect digital model. It was a sketch on a fragile, imperfect medium. Think of a rough diagram scratched onto a wax tablet that could be wiped clean with a slip of the hand, or a drawing on papyrus that could tear, fade, or be eaten by insects. Even clay tablets, while durable once fired, were heavy, difficult to edit, and nearly impossible to reproduce with perfect accuracy. These were the blueprints of their day, and they were fraught with problems. The first major issue was the medium itself. A wax tablet surface was uneven, and the stylus could catch, turning a straight line into a jagged error. Papyrus had a fibrous texture that could distort a carefully inked curve, translating a three-dimensional, volumetric idea, like the complex curvature of a dome onto a flat, flawed surface was a recipe for misinterpretation. A master builder might draw an arch to represent a vault, but how does that drawing convey the subtle torsion or the precise angle of every stone? It couldn't. The information loss was enormous. Then there was the problem of scale. Without standardized rulers or graphing techniques, scaling a small sketch up to a life-sized structure was an exercise in guesswork. A tiny, almost imperceptible error in the angle of a load-bearing wall on a papyrus scroll could become a several-foot mistake when magnified to the scale of a palace, leading to instability and collapse. This introduced what we can call a translation error. Every time you move a design from the mind to a sketch to the actual materials, you risk introducing mistakes. The ancient method of direct execution was brilliant because it eliminated this unreliable middle step. It cut out the draft. The mind of the designer was connected directly to the hands of the builder, with no fragile, ambiguous drawing in between to mislead or confuse. The plan existed in the shared understanding of the master and the team, and it was tested and refined in real time against the unforgiving reality of stone and mortar. This directness wasn't a primitive shortcut. It was a sophisticated strategy to avoid a major source of potential failure. By building full scale from the start, they bypassed the inherent limitations of their own primitive drafting technology, ensuring that the only blueprint that truly mattered was the one being forged correctly and permanently in the enduring materials themselves. Nowhere is the power of this hands-on, responsive approach more stunningly visible than in the mountains of Peru, where the Inca Empire left behind what might be the ultimate argument against the necessity of blueprints. The walls of Machu Picchu and the foundations of Cusco are not just ruins, They are a masterclass in a unique form of engineering called polygonal ashlar masonry. To stand before these structures is to witness something that seems to defy the laws of physics. Enormous blocks of stone, some weighing many tons, are fitted together with such seamless precision that you cannot slide a piece of paper between them. But here's the catch that baffles modern engineers. The stones are not uniform rectangles. They are a chaotic-looking assortment of polygons, each with multiple sides and strange, irregular angles. This is not the result of haphazard pile driving. This is a technique of breathtaking sophistication, a three-dimensional stone puzzle of immense complexity, achieved entirely without drawn plans. The process was what we might call surgical. A team of masons would begin with a rough-hewn stone. They would not have a template or a pattern to follow. Instead, they would maneuver it into a gap in the growing wall, carefully noting where it made contact with its neighbors. Then began the meticulous, iterative dance of fitting. Using harder stone tools, they would peck away at the contact points, slowly shaping the new block to mirror the exact contours of the ones already in place. They would fit, mark, remove, carve, and fit again, over and over. It was a conversation between the new stone and the existing wall, a dialogue conducted through trial and error until the fit was perfect. This wasn't a slow, inefficient method. It was the very source of the method's genius. Think of it like a master key cutter who doesn't use a machine, but instead files a blank key by repeatedly testing it in the lock, learning the precise shape from the lock itself. For the Inca, the wall was the lock, and each stone was a key being shaped to fit perfectly. This approach created structures with a miraculous property: earthquake resistance. Peru is one of the most seismically active regions on Earth, and a rigid, mortared wall would crack and crumble when the ground shook, but an Inca wall is different. Because the stones are interlocked in such an intricate, jigsaw-like pattern, they have no rigid joints to fail. When an earthquake strikes, the entire wall dances. The stones sway and settle against each other, dissipating the energy of the tremor through their complex interactions. Once the shaking stops, they often settle back into a stable, and sometimes even tighter, configuration. A blueprint for such a wall would have been not just difficult to create, but completely useless. How could you possibly draw, in 2 dimensions, the exact, irregular shape of every single one of thousands of stones? And even if you could, how would a mason hundreds of miles away in a quarry know how to carve a stone to fit a gap he had never seen? The intelligence was not captured on paper. It was embedded in the process itself. It resided in the skill of the masons, in their patient, tactile feedback loop with the stone, and in the emergent order of the wall as it grew. The Inca redefined precision. For us, precision often means conformity to a predetermined, measurable standard. For them, precision meant achieving a perfect, resilient fit within a dynamic, living system. Their walls are not precise by our abstract, planar standards, but they are precisely, perfectly adapted to their environment and purpose in a way that continues to humble modern engineering. But even with modular kits and responsive building, you might wonder how ancient architects could possibly hold the design for an entire temple or palace in their head. The secret lies in a universal language they all spoke fluently, the language of geometry and proportion. This wasn't about memorizing thousands of specific measurements. It was about mastering a handful of powerful, abstract rules that governed relationships. Think of it as the difference between trying to remember every single word of a speech versus understanding the core themes and being able to speak eloquently on the spot. Ancient engineers worked with these core themes of shape and ratio. they understood that certain proportions were inherently pleasing to the human eye and, just as importantly, inherently stable. The Pythagorean theorem wasn't just a math puzzle. It was a practical tool for ensuring a builder could create a perfect right angle for a foundation using nothing more than a knotted rope. The golden ratio, approximately 1.618 to 1, was observed in nature from the spiral of a nautilus shell to the arrangement of leaves on a stem, and was consciously applied to create buildings that felt naturally beautiful and harmonious. These were not rigid formulas to be slavishly followed, but rather guiding principles, a mental toolkit for creating order out of chaos. A master architect wouldn't need to provide a detailed drawing for every column in a Greek temple. Instead, he would establish a single, simple rule: the height of each column must be 6 times its diameter. This one instruction, easily remembered and communicated, could then be applied by stonecutters and masons across the entire project. The actual diameter might change slightly depending on the quarry or the column's position, but the proportional relationship remained constant, ensuring visual and structural coherence. This system was brilliantly scalable. The same set of proportional rules used for a small shrine could be effortlessly expanded to design a massive cathedral simply by increasing the base measurement, or module. The entire building would grow organically, maintaining its perfect balance because every part was related to every other part through this shared mathematical language. This approach offered an incredible freedom within a framework. A builder wasn't trapped by a fixed plan. If they discovered that a particular type of stone was only available in slightly shorter blocks, they could adapt. They could adjust the module slightly, and as long as they maintained the proportional rules, the column height is still 6 times its new diameter. The design would remain sound and aesthetically unified. The intelligence was in the system itself, not in a voluminous set of instructions. This reliance on proportional logic meant that the most complex designs could be held in the mind and communicated through a few elegant principles, connecting the grandeur of their constructions directly to the mathematical order they perceived in the universe itself. This collaborative spirit transformed a sprawling construction site into something far greater than the sum of its parts. It became a living, thinking organism. Picture the scene at the base of a rising pyramid, not a scene of chaotic noise, but a symphony of coordinated activity. Quarrymen, with an intimate knowledge of the bedrock, selected stones not just for size, but for their specific place in the structure, understanding how a stone's grain would bear weight. Haulers developed ingenious techniques, using rollers and levers, their expertise turning an impossible task into a rhythmic, manageable process. High on the rising walls, the masons, with their keen kinesthetic intelligence, would call out for adjustments, their hands feeling the perfect fit as the haulers below responded in real time. This wasn't a chain of command. It was a continuous feedback loop where information flowed in all directions. The intelligence was not bottled up in a single mastermind, but was distributed across the entire workforce. Each specialist was an expert in their domain, and the project thrived on the cross-pollination of their distinct skills. A problem that might stump an architect alone, like an unexpected fissure in the foundation, would be met with a communal solution. Quarrymen might suggest a type of stone known for its flexibility to bridge the gap. The mason would propose a specific cutting technique to interlock with the surrounding rock, and the haulers would devise a way to maneuver the unusual block into place. Solutions emerged organically from the collaboration, often leading to innovations that no single person would have conceived in isolation. This decentralized model created incredible resilience. In a top-down system, if the chief architect fell ill or was lost, the entire project could stall, trapped by a knowledge vacuum. But in this distributed model, the knowledge lived in the hands and minds of dozens of key figures. The loss of any one individual was a tragedy, but not a catastrophe for the project. The collective understanding of the goal and the methods was so deeply ingrained in the community that the work could continue, the shared purpose guiding the team forward. This stands in stark contrast to the siloed nature of many modern projects, where strict adherence to a central plan can sometimes stifle the very on-the-ground expertise that could prevent a problem. The ancient building site was a testament to the power of the collective mind, where every participant was not just a pair of hands, but a vital node in a vast, adaptive network of intelligence. This capacity for immediate adaptation gave ancient construction sites a dynamic energy that is hard to fathom in our world of permits and change orders. A modern construction project can grind to a halt for weeks if an unexpected geological feature is discovered during excavation, requiring teams of engineers to return to their desks, run new simulations, and produce a stack of revised drawings. For the builders of antiquity, the discovery of a hidden spring or an unusually soft patch of earth was not a crisis. It was simply the next piece of information to be integrated into the evolving design. The solution was generated on the spot, informed by the collective experience of the master builders present. They might choose to divert the water into a new drainage channel that became part of the foundation, or they might decide to widen the base of the wall to distribute the weight more effectively over the unstable ground. The problem and its solution existed in the same time and place, handled by the same people, creating a seamless flow of continuous improvement. This real-time responsiveness meant that the final structure was, in a very real sense, a product of its own environment, custom-fitted to the unique challenges of the site in a way a prefabricated design could never be. Every obstacle encountered and overcome during construction actually made the building stronger and more uniquely suited to its location. This process mirrors the principles of modern Agile development, where products are built and refined through successive iterations based on user feedback, rather than being fully specified in a rigid plan before a single line of code is written. The ancient builders were practicing a form of Agile engineering, where the user feedback came directly from the materials, the landscape, and the growing structure itself. This Agile approach turned potential disasters into creative opportunities. Imagine a team carving a massive obelisk from a quarry. After months of painstaking work, a hidden flaw in the granite causes a critical crack to appear just before the monolith is freed. In our modern context, this would likely mean the abandonment of the entire costly project. But for the ancient Egyptians, this wasn't a total loss. They would pivot instantly. That beautifully carved but fractured obelisk might be cut down into several perfectly good statues or a series of smaller columns for a temple entrance. The skill and labor invested were never wasted. They were simply redirected. This mindset of resourcefulness and flexibility meant that very little was ever truly lost. The design was not a fragile, precious idea that had to be protected at all costs. It was a living, malleable strategy that could bend and shift without breaking. This acceptance of change built a remarkable resilience into the entire enterprise. It was an understanding that the perfect plan is not the one that is followed without deviation, but the one that adapts most successfully to the unpredictable nature of reality. By embracing the inevitable surprises of construction, these master builders created final products that were not merely executions of an initial vision, but were the refined, battle-tested results of a continuous conversation with the real world. This profound shift in how we build began not with a bang, but with the quiet scratch of a pen on parchment during the Renaissance, as thinkers like Leon Battista Alberti began to argue that architecture was an intellectual art, separate from the manual labor of construction. A subtle but decisive wedge was driven between the mind that conceives and the hands that create. The invention of the printing press then accelerated this division, making it possible to mass-produce identical sets of instructions and distribute them to far-flung construction sites. For the first time, the plan could exist independently of the planner and the builder. This was a revolution in control and scalability, but it came with a hidden, steep cost: the gradual erosion of tacit knowledge. Tacit knowledge is that deep, intuitive understanding of a craft that is almost impossible to put into words. It's the mason's feel for how a specific limestone will weather after a harsh winter, or the carpenter's instinct for the exact moment a joint is tight enough without being forced. This wisdom, accumulated through generations of hands-on experience, began to be sidelined. It was considered messy, unquantifiable, and old-fashioned compared to the clean, precise lines of a technical drawing. Knowledge that was once carried in the muscles and senses of the artisan was now expected to be fully captured in the explicit, codified instructions of a blueprint. The architect, now often a gentleman scholar working in a comfortable studio far from the dust and noise of the quarry or the foundry, could design complex structures based on mathematical principles and aesthetic ideals. But in this new separation, they lost the intimate, real-time feedback loop that had been essential for millennia. They no longer felt the heft of the materials they specified or witnessed how their designs behaved under the actual stresses of wind, rain, and gravity during the building process. This disconnect created a new hierarchy, a class system within the world of construction. The thinker, the architect, was elevated while the doer, the stonemason, the blacksmith, the carpenter, was demoted to a mere executor of a vision they had no part in shaping. Their hard-won tacit knowledge was no longer sought after. Their role was reduced to following the lines on the page. This schism could lead to a dangerous reality gap. A design might be geometrically perfect and aesthetically stunning on paper, but problematic or even unbuildable in reality. An architect might specify a certain type of beam for its beauty, unaware that it has a tendency to warp under load in a specific climate. The builder on the ground, possessing the tacit knowledge to recognize this flaw, would often have no authority to suggest a change. They were forced to build the flaw into the structure, leading to future repairs or failures, or to improvise a fix that might compromise the original design. This separation of conception from execution is a trade-off that continues to shape our built environment today. We gained unprecedented control and the ability to build on a colossal scale, but we may have lost the resilient, adaptive intelligence that comes from a deep, collaborative dialogue between the mind, the hand, and the material world. The cost of this divorce is something we are still calculating with every building that fails prematurely or feels alienated from its surroundings. Now, consider the incredible mental gymnasium this hands-on process created for the ancient mind. Without the crutch of a detailed drawing to refer back to, a master builder was forced to develop an internal, three-dimensional map of the entire structure. This wasn't just about remembering a list of steps, it was about cultivating a powerful, dynamic spatial reasoning ability. Imagine the challenge of constructing something as geometrically complex as a Gothic rib vault. A modern engineer has cross-sectional diagrams and computer models showing every intersecting arch and keystone. The medieval master mason had to hold that entire intricate web of stone in his mind's eye. He needed to visualize not just the final form, but the precise sequence of construction which stone had to be placed before another, how the temporary wooden centering would support the arches until the keystone locked everything into place, and how the weight would ultimately transfer through the entire system. This constant, demanding exercise in mental visualization was like a daily workout for the brain's parietal lobe, the region heavily involved in manipulating and navigating spatial relationships. This honed their ability to think in volumes and forces, not just in lines on a page. They weren't just following instructions. They were living inside the geometry of their creation long before the first stone was ever laid. This deep mental engagement meant that their understanding of the structure was fluid and holistic. They could mentally rotate components, foresee potential points of weakness, and run through what-if scenarios in their head. A builder could stand at the base of a rising wall and, by looking at the angle of a single course of stones, intuitively predict the stress distribution 10 courses higher. This spatial intelligence was further amplified by a highly trained memory, but not the kind of memory we typically think of today. In a world before written instructions were commonplace, the primary channels for learning were auditory and tactile. A master's verbal instructions the specific sequence for mixing a particular mortar, the poetic names for different types of joints, the rhythmic chants used by haulers to coordinate their efforts had to be memorized with exacting precision. This wasn't rote memorization, it was the retention of complex, interconnected systems of knowledge. An apprentice's memory was also deeply tactile. They remembered the feel of a correctly set stone, the specific resistance of a well-seasoned piece of timber under a saw, the sound a mallet made when a joint was perfectly tight. These sensory impressions were stored as a library of physical references, a database of what right feels like that guided their hands. This combination of superb spatial reasoning and a richly textured, multi-sensory memory created mental models of projects that were far more comprehensive than any static blueprint. Their internal representation included the weight, the texture, the sound, and the behavior of the materials under load. It was a living, breathing simulation running in the builder's mind, continuously updated by the real-world feedback from the construction site itself. This cognitive discipline didn't just make them good builders, it forged them into intuitive engineers of remarkable capability, whose understanding of their craft was as much an art of the mind as it was of the hand. This inherent connection to place and material that defined ancient engineering naturally fostered a level of sustainability that we are only now, with our advanced technology, striving to recreate. When you cannot rely on complex logistics to ship materials across continents, your first and only option is to look to the landscape around you. This wasn't a philosophical choice about reducing carbon footprints. It was a simple, pragmatic reality. The very constraints that might seem like limitations became the source of an incredibly efficient and resilient building ethic. A community living in a forest would become masters of timber framing, understanding the different strengths of oak for beams and cedar for shingles. A civilization nestled in mountains would develop an unparalleled expertise in stonework. This deep local knowledge meant that builders selected materials not just for their availability, but for their proven performance over generations. They knew which local stones could withstand freeze-thaw cycles, which woods were most resistant to rot, and how the local clay would behave when fired into bricks. The structures that emerged were, by their very nature, perfectly adapted to their environment. A stone house in a windy, coastal region would be built low and thick-walled to withstand the gales, while a bamboo structure in a tropical climate would be raised on stilts for ventilation and flood protection. The design was a direct response to local conditions, using locally understood materials, creating a built environment that was inherently harmonious with its surroundings. This stands in stark contrast to much of modern construction, where the same glass and steel tower can be plopped down in Dubai, London, or Singapore, often requiring immense energy to heat, cool, and maintain in climates they were never designed for. The ancient approach was one of bioregionalism by default. The building literally grew from the soil it stood on. This direct relationship also enforced a radical form of resource efficiency. Without the guarantee of a steady supply chain delivering more materials next week, every piece was precious. A stonemason wouldn't simply discard a block that had an unusual shape or a slight flaw. Instead, they would see the unique character of that stone as an opportunity. They would turn it, shape it, and find the perfect niche for it in the wall where its peculiarities became strengths. This mindset of waste not, want not was born from necessity, but it resulted in construction sites that generated very little debris. Consider the process of building a dry stone wall where no mortar is used. The builder must carefully select each stone, turning it over and over in their hands, assessing its shape from every angle to find the one position where it locks perfectly with its neighbors. The goal is to use the stone exactly as it is, with minimal cutting or shaping. Any small chips that did break off during the process wouldn't be swept away as trash. They would be used as chinking, the small stones hammered into tiny gaps to add stability. This created a virtually zero-waste process. Even in larger projects like the construction of a cathedral, the efficiency was remarkable. The offcuts from large stone blocks would be used for smaller sculptures, rubble would be packed into foundations, and sawdust from woodworking would be mixed into daub or used as fuel. Nothing was considered surplus until every possible use had been exhausted. This circular economy wasn't a designed system. It was an emergent property of a mindset that valued materials and recognized their inherent worth and the labor required to produce them. The entire philosophy was one of working with what you have, of making the most of the gifts of the local environment. This ancient, constraint-driven approach offers a powerful lesson for our current era of ecological crisis. While we develop complex technologies for recycling and green certification, the most profound sustainable principle might be the simplest: know your place, use what it provides, and waste nothing. It is a lesson in humility and intelligence, written not in policy documents, but in the enduring stones of the past. This organic approach to building gave rise to an aesthetic quality that is deeply human and profoundly moving. When you walk through the cobbled streets of an old European town and run your hand along a stone wall, you are not touching a flat, monotonous surface. You feel the subtle undulations, the unique chisel marks of a mason who worked that stone centuries ago. Each irregularity, each slight deviation from a perfect plane is not a flaw. It is a signature. This is the beauty of the handmade, a character that emerges precisely because the process was guided by human intuition and a responsive dialogue with the material, not by the rigid dictates of a pre-drawn plan. In Japan, there is a concept known as wabi-sabi, which finds beauty in imperfection, impermanence, and the marks of age and use. While the term itself is culturally specific, the principle it describes is universal in the world of ancient craftsmanship. A medieval cathedral floor, worn down into gentle dips by the footsteps of millions of pilgrims over hundreds of years, possesses a wabi-sabi quality. The stones tell a story of devotion and time, the uneven settling of a timber frame over the centuries, creating a floor that slopes ever so slightly, doesn't make the building defective, it makes it authentic. It bears witness to its own history and its ongoing conversation with gravity and the elements. This stands in stark contrast to the sterile perfection of many modern constructions, where every surface is flawlessly flat, every corner a precise 90 degrees, and every component interchangeable with another. While this machine-like precision has its own kind of awe, it can often feel cold and anonymous. A building made entirely of mass-produced parts following a digital file lacks a narrative. It doesn't tell you how it was made or who made it. There are no fingerprints left in the concrete, no unique variations that speak to the individual who shaped a particular stone. The ancient structure, however, is brimming with such stories. Look closely at the carved capitals on the columns of a Romanesque church. No two are exactly identical. The leaves might be slightly fuller on one, the faces on the figures might carry different expressions. This variation is not a sign of poor quality control. It is evidence of the individual artisans who worked on them, each bringing their own skill, their own mood, and their own interpretive flair to the task. The building becomes a collective autobiography of its creators. This connection to the human hand creates spaces that are not just visually interesting but emotionally resonant. There is a warmth, a soulfulness that we intuitively respond to. We feel the presence of the people who built it. This aesthetic of imperfection is paradoxically a hallmark of true mastery. It reflects a confidence that allows for the happy accident, the embrace of the material's inherent character, and an understanding that beauty is not synonymous with mathematical perfection, but with life, history, and the unmistakable touch of the human spirit. Of course, we must temper our admiration for these ancient methods with a sobering dose of reality. For all its profound strengths, this blueprint-less approach was a high-stakes endeavor, a tightrope walk without a safety net. The potential for catastrophic failure was an ever-present shadow looming over every ambitious project. A single miscalculation, a misunderstood instruction passed down the chain of apprentices, or an overestimation of a material's strength could lead to a sudden, horrifying collapse. The sound of crumbling stone and the loss of life were the brutal price of experimentation in an age without structural analysis software. We have to remember that history is a filter, and it is not a fair one. The phenomenon known as survivorship bias means we only see the triumphs, the pyramids, the Parthenon, the aqueducts that defied time. We do not see the countless temples, towers, and bridges that fell, their ruins scavenged for materials or simply buried by the centuries. Their stories and the hard lessons learned from their failures are largely lost to us. We gaze in wonder at the Colosseum, but we never hear about the amphitheater in a distant Roman province that collapsed during its inaugural games, a tragedy born of a local builder misjudging the load-bearing capacity of a key arch. These silent failures are the hidden counterpoint to the majestic successes. This inherent risk is precisely why the blueprint gradually gained dominance. As human ambition pushed towards ever greater complexity toward soaring Gothic cathedrals with their delicate walls of glass and vast, unsupported domes, the intuitive trial-and-error method began to show its limits. The consequences of a mistake became too great to bear. The development of detailed plans was in large part a safety revolution. It was the engineering world's way of saying, let's think this through completely before we commit thousands of tons of stone to the sky. The ability to pre-visualize a structure on paper, to calculate load paths and stress points in advance, introduced a critical layer of foresight. It allowed architects to identify potential points of failure on a two-dimensional surface long before those weaknesses could manifest in three-dimensional tragedy. This shift represented a move from reactive problem-solving, fixing a crack as it appeared, to proactive risk mitigation, anticipating problems before the first foundation stone was ever laid. This safety function is the bedrock of the modern engineering ethos. It is the reason we can build skyscrapers that sway safely in the wind and bridges that span chasms with confidence. The blueprint and its digital descendants are not just tools of control. They are instruments of responsibility designed to protect the lives of both the builders and the eventual occupants. So, while we can rightly celebrate the intuitive genius of the ancients, we must also acknowledge this critical trade-off. Their method fostered incredible adaptability and deep material wisdom, but it carried a terrifying vulnerability. The rise of the plan was not merely a change in technique. It was a necessary evolution towards greater predictability and safety, a vital lesson written in the invisible ink of all the structures that did not survive to tell their tale. So, how did we move from this world of intuitive, hands-on creation to our current reliance on the abstract diagram? The shift wasn't a sudden collapse, but a gradual convergence of powerful forces that reshaped the very philosophy of building. The first tremors of change began in the minds of Renaissance thinkers, a period that witnessed a profound intellectual rebellion against the collective spirit of the Middle Ages. This new era celebrated the individual genius, the lone mastermind whose vision could transcend the work of mere craftsmen. For the first time, the architect was not just a senior mason. He was an artist and a scholar, often educated in the classics and well-versed in mathematics. Figures like Leon Battista Alberti and Filippo Brunelleschi began to argue that architecture was not a manual trade but an intellectual discipline, a science that could be reasoned out on paper before a single stone was cut. This was a radical departure. The design process was lifted from the dusty construction site and into the clean, well-lit studio. It was here that the blueprint began its ascent, not as a mere aid, but as the primary vessel for a grand idea. And no one embodied this new ideal more powerfully than Leonardo da Vinci. His notebooks are a breathtaking testament to this shift. They are filled not with rough sketches, but with incredibly detailed, exploded view drawings of machines, anatomical studies, and architectural plans of stunning complexity. Leonardo was visualizing forces, mechanisms, and structures on paper with a precision that had never been attempted before. He was conducting theoretical engineering, working out problems of stress and load in 2 dimensions, elevating design from a craft to a theoretical science. The blueprint was no longer just a memory aid. It was becoming the birthplace of innovation itself. But intellectual curiosity alone wasn't enough to cement the blueprint's dominance. The second great force was the grim practicality of warfare. As cannons grew more powerful in the 15th and 16th centuries, the old, high-walled castles of the medieval era became death traps. A new type of defense was needed. The Star Fort, with its low, thick, angled walls designed to deflect cannonballs and provide overlapping fields of fire for the defenders. These fortifications were geometrically complex, and their effectiveness depended on absolute precision. A king couldn't rely on the tacit knowledge of local masons to build a fortress on a distant frontier. A single misplaced angle could create a deadly blind spot for the enemy to exploit. The military needed standardization and control. Detailed, accurate plans became essential. They could be sent to engineers across a kingdom or an empire, ensuring that a fort in Flanders was built to the exact same specifications as one in northern Italy. The blueprint became an instrument of imperial power, allowing for the rapid, reliable replication of complex defensive works that were essential for controlling territory. This military demand for precision and uniformity provided a powerful, practical push for the development and refinement of technical drawing. Then came the tidal wave that would sweep the old ways aside entirely, the Industrial Revolution. This new era wasn't about building unique cathedrals or palaces. It was about building thousands of identical machines, rifles, and eventually railway bridges. The core principle of industrialization is interchangeability. A part made in one factory must fit perfectly with a part made in another, perhaps hundreds of miles away. This was impossible with the old craft-based methods. You cannot have 1,000 workers in different cities intuitively shaping metal components to feel right. The only way to achieve this miracle of mass production was through the absolute tyranny of the plan. Detailed, dimensioned drawings became the universal language of industry. They allowed an engineer in Birmingham to design a steam engine and have every piston, every valve, and every bolt manufactured separately by different specialized firms, with the absolute confidence that they would all assemble into a functioning whole. The invention of lithography and later blueprinting itself, a chemical process that produced white lines on a blue background, hence the name, made it cheap and easy to produce countless identical copies of these plans. This was the final piece of the puzzle. The blueprint was now reproducible, portable, and precise. It enabled control on an unprecedented scale, predictability in a world of chaotic variables, and scalability that allowed for projects of a size and complexity that would have been unimaginable to the ancient world. This transition was a trade, a bargain we made with the future. We gained the power to build the modern world, but we began to lose the intimate, resilient, and deeply human connection to the act of creation that had defined engineering for millennia. It's a fascinating twist of history that our most advanced fields of creation are now circling back to principles that would have been second nature to an ancient mason. After centuries of moving toward ever more detailed pre-planning and rigid specifications, a counter-movement has emerged championing flexibility, adaptation, and direct feedback. Nowhere is this more evident than in the world of software development. For decades, the standard approach was the waterfall model, a linear, sequential process where every requirement was meticulously documented in a massive specification document before a single line of code was written. It was the ultimate blueprint, a digital equivalent of a full set of architectural drawings. But developers found that this process was brittle. By the time a multi-year project was completed, the market needs had often changed, the technology had evolved, and the final product was already outdated. The response to this frustration was the Agile Manifesto, a philosophy that consciously rejects the idea of a fixed final plan. Instead, Agile breaks down development into short, iterative cycles called sprints. A small team builds a basic, working version of a feature in a matter of weeks, not years. They then immediately show this prototype to the users, gather direct feedback on what works and what doesn't, and then use that real-world input to plan the next cycle of improvements. This is not so different from a medieval master builder erecting a section of a wall, observing how it settles after a winter, and then adjusting the design for the next section based on that lived experience. The intelligence is generated through doing, not just through theorizing. The Agile team, much like the collaborative workforce on an ancient site, operates as a self-organizing unit, solving problems collectively and adapting to new information as it emerges. The plan is a living document, constantly evolving, much like the building that served as its own blueprint. This shift from a rigid, top-down blueprint to a flexible, iterative process is a direct echo of the ancient understanding that the best designs emerge from a dialogue with reality, not from an attempt to impose an abstract ideal upon it. This return to tactile, iterative creation is equally visible in the physical world through the revolution of rapid prototyping and three-dimensional printing. For much of the industrial age, designers were trapped in a similar cycle of abstraction. They would create detailed drawings or computer models of a new product, a car part, a medical device, a piece of furniture, and then send those plans off to a factory to be tooled and manufactured. The first time the designer would actually hold the object in their hands might be months later, after thousands of dollars had been spent on creating molds and setting up production lines. If there was a flaw, a subtle ergonomic issue that wasn't apparent on the screen, or a structural weakness, the cost of change was enormous. Three-dimensional printing shatters this barrier. Now a designer can create a digital model and within hours hold a physical, full-scale prototype. They can feel its weight, test its grip, see how its parts interact, and subject it to real-world stresses. This re-establishes the vital kinesthetic feedback loop that ancient engineers relied upon. The designer is no longer separated from the material reality of their creation by a stack of drawings and a lengthy manufacturing process. They can engage in that direct tactile dialogue. They can print a version, test it, break it, learn from its failure, and then immediately modify the digital model and print another iteration. This rapid cycle of creation and testing allows for a form of evolution in design. The final product isn't just the execution of an initial idea. It is the result of dozens of small adaptations and improvements, each informed by physical interaction. This is precisely the same process an Inca mason used when carefully shaping a stone to fit its neighbors through repeated trial and error. The modern designer, armed with a three-dimensional printer, is rediscovering the power of learning through direct manipulation of the material, proving that some forms of knowledge can only be gained through the hands. This direct, hands-on involvement in the creative process fundamentally transformed the psychological relationship between the craftsman and his work. When your task is not to simply follow a line on a page but to actively shape the outcome through your own judgment, the work ceases to be a job and becomes a form of personal expression. A stonemason fitting a block into an Inca wall wasn't just placing a component. He was solving a unique, three-dimensional puzzle that would exist for centuries. Every tap of his hammer, every minute adjustment, was an application of his hard-won skill and intuition. This autonomy granted a level of ownership that is difficult to replicate in a system governed by strict specifications. The wall was not just a wall, it was his section of the wall, a permanent testament to his individual ability and care. This sense of responsibility for the final product naturally cultivated a powerful pride in craftsmanship. The motivation to excel came not from an external supervisor demanding compliance with a plan, but from an internal drive to see one's best work immortalized in stone. The desire to create something beautiful, something stable, something that would earn the respect of their peers and honor their master, was a far more potent motivator than any fear of punishment. This deep personal connection to the work meant that cutting corners was unthinkable. A flaw in the stone, a poorly set joint, would not just be a mark against the project, it would be a personal failure, a blemish on their own legacy. This psychological investment was the invisible ingredient that ensured an unparalleled commitment to quality. The finished structure, therefore, was more than an architectural achievement. It was a collective mosaic of individual dedication, a physical manifestation of the pride and skill of every single person who contributed to its creation. This stands in stark contrast to the alienation that can occur in modern, highly segmented construction. When a worker on a contemporary site spends their day installing identical prefabricated panels according to a detailed manual, their role can feel transactional. They are one link in a long chain, executing a small, repetitive part of a vision conceived by someone they will never meet. The connection between their individual effort and the grandeur of the final building can become abstract and distant. It is easier to feel like a replaceable cog in a vast machine, where personal initiative is often discouraged in the name of adhering to the plan. The ancient model, by placing immense trust in the craftsman's judgment, tapped into a profound source of human fulfillment, the innate desire to see our skills make a tangible, lasting difference in the world. This fulfillment was not a happy byproduct. It was the very fuel that powered the meticulous, painstaking work that resulted in structures of such enduring quality. The human spirit, when granted autonomy and a clear line of sight between effort and outcome, is capable of extraordinary things. This psychological dimension, this deep-seated need for meaningful work, may be one of the most powerful and overlooked reasons why these ancient wonders continue to stand as testaments not just to engineering, but to the human capacity for excellence when truly engaged. This brings us to a critical crossroads in our own time, a point where the ancient wisdom of the hands meets the modern power of the mind. Our current system for training engineers and designers is a product of the very revolution that prioritized the blueprint. We have built magnificent universities that are temples to abstract theory, where students spend years mastering complex mathematics, physics, and computer-aided design. These are undeniably powerful tools, but they represent only one half of the ancient equation. The other half, the deep, tactile, intuitive understanding of materials and forces, is often relegated to a single lab course or overlooked entirely. We are producing brilliant theoreticians who can simulate a bridge's load capacity with stunning accuracy on a screen, but who may have never felt the heft of a steel I-beam or mixed a batch of concrete with their own hands. This creates a dangerous disconnect. A designer might specify a material based on a date or sheet without any visceral understanding of how it behaves under a hammer, how it weathers in the rain, or how it feels to assemble. The ancient model offers a powerful corrective, a return to the integrated path of the master and apprentice, a rebalancing of the scales between abstract calculation and embodied experience. Imagine a different kind of engineering classroom. Alongside the banks of computers running simulation software, there would be workshops filled with raw materials, blocks of wood, sheets of metal, bags of sand and cement. The curriculum would be fundamentally redesigned so that theoretical lessons are immediately followed by physical experiments. Instead of just calculating the tensile strength of a material from a textbook, students would be tasked with building a simple truss bridge out of balsa wood and then progressively loading it until it fails. The sound of the wood splintering, the sight of the specific joint that gave way first, these sensory experiences create a visceral understanding of failure modes that a graph on a screen can never fully convey. They would learn the difference between a rigid and a flexible connection, not just as a mathematical concept, but as a feeling in their hands when they try to wiggle the joint. This hands-on work rebuilds the very kinesthetic intelligence that was the secret weapon of ancient builders. It trains the body to be a sensor, to understand weight, balance, and structural honesty through direct engagement. An engineer who has physically struggled to lift a heavy object understands center of gravity in a more profound way than one who has only solved equations for it. This approach would also revive the invaluable role of tacit knowledge. In a modern apprenticeship model, a seasoned professor or a visiting master craftsperson wouldn't just lecture, they would work alongside the students. The learning would happen through observation and mimicry. A student might watch how the expert subtly taps a chisel to split a stone along its natural grain, learning the precise sound and feel of a successful strike. They would absorb the unspoken tricks of the trade, the way to test the slump of concrete to know if it has the right water content, or the instinct for when a weld has properly penetrated. This knowledge is almost impossible to codify in a textbook or a lecture slide. It must be transmitted through shared experience. It's the difference between reading about how to ride a bike and actually feeling the balance as you pedal. By integrating this master-apprentice dynamic into formal education, we would create engineers who are not just calculators but intuitive problem solvers, capable of sensing a problem before it appears on a sensor readout. The benefits of this shift would extend far beyond technical skill. It would foster a deeper respect for materials and sustainability. A student who has spent days planing a piece of wood to a smooth finish develops a relationship with that material. They understand its value, its unique character, and they are far less likely to specify its wasteful use in a design. This reconnection with the physical world could spark a new wave of bio-inspired design, where engineers, having closely observed the efficient structures in nature, from the hollow bones of a bird to the deep roots of a tree, begin to emulate those principles in their work. Furthermore, this blend of mind and hand is the true path to mastery and innovation. History shows us that some of the greatest breakthroughs occur at the intersection of disciplines, when a theoretical insight is tested and refined through physical experimentation. The Wright brothers were not just theorists, they were brilliant tinkerers who learned about lift and drag by building and crashing countless gliders. By giving our future engineers and designers the gift of both deep theoretical knowledge and profound hands-on intuition, we are not taking a step backward. We are unlocking a new generation of builders who can wield the awesome power of modern technology without losing the ancient, enduring wisdom of the hand. They will be the ones who can design a building that is not only structurally sound on paper, but is also a joy to inhabit, that is resource efficient, and that feels truly rooted in its place, a testament to the harmonious blend of human intellect and earthly material. But to truly grasp the ancient mind, we must understand that their most profound engineering principles were often hidden in plain sight, woven into the very fabric of their stories and sacred myths. For these builders, there was no hard line between the practical knowledge of how to construct a stable arch and the mythological understanding of how the world was constructed. These domains were not separate, they were two sides of the same coin, a unified system for making sense of the universe. Consider the legendary figure of Daedalus, the master craftsman of Greek myth who built the labyrinth to contain the Minotaur. On the surface, this is a thrilling story of heroes and monsters, but for an apprentice engineer, it was also a sophisticated lesson in complex geometry. The labyrinth was described as a structure so cunningly designed that once inside, no one could find their way out. This wasn't just a magical prison, it was a metaphorical blueprint for understanding non-repeating patterns and structural deception. The myth encoded a critical technical concept: how to design a path that constantly turns back on itself, creating confusion and disorientation without dead ends. A master teaching this concept wouldn't need a complex mathematical diagram. He could simply recount the tale of Theseus and the ball of string. The story itself became a powerful mnemonic device, a memorable package that carried the essence of a complex architectural idea across generations. The hero's journey through the twisting corridors was a narrative representation of the spatial problem, making an abstract principle tangible and unforgettable. This fusion of story and skill extended far beyond Greece. Across the ancient world, myths served as the hard drives of pre-literate societies, storing vast amounts of practical and environmental data in a durable, easily transmissible format. An Aboriginal Australian songline, for instance, is a complex oral map embedded in a series of songs and stories that describe the paths and landmarks across vast stretches of the continent. To sing the song is to navigate the land, with each verse corresponding to a specific feature in the terrain. This is a brilliant system for encoding topographical knowledge, the location of waterholes, the types of edible plants, the behavior of animals, within a memorable cultural narrative. The story ensures the survival of the knowledge. The knowledge gives the story its power and purpose. Similarly, Norse myths are filled with incredibly detailed descriptions of shipbuilding, from the selection of specific types of oak for the keel to the intricate process of clinker construction, where overlapping planks are riveted together for flexibility and strength in rough seas. The adventures of Viking heroes aboard their longships were not just entertainment, they were practical demonstrations of naval engineering set within an epic frame. The myth of Thor's hammer, Mjolnir, which always returned to his hand, can be seen as a poetic expression of the smith's quest for the perfect balance and weight in a tool or weapon, a concept every blacksmith would understand intimately. This intertwining provided a rich, multi-layered framework for learning. A young person listening to these stories was not just passively absorbing a tale, they were being initiated into a world of practical wisdom. The narrative provided the context, the emotional hook, and the moral dimension that made the technical knowledge stick. Learning became a process of uncovering hidden meanings. The story of Icarus, who flew too close to the sun despite his father Daedalus's warnings, is a poignant lesson about the limits of materials. The wax that held the feathers of his wings together melted, causing him to fall. This is a powerful allegory about understanding the properties of your materials and the dangers of overreaching, a fundamental principle of engineering ethics. The myth teaches respect for the constraints of the physical world in a way that a simple warning never could. It connects a technical failure to a profound human drama, embedding the lesson deep in the listener's memory. This method of teaching through layered narrative created engineers who thought holistically. They didn't just see a building as a collection of stones, they saw it as part of a larger cosmic order, a story written in stone. The pyramid was not just a tomb, it was a representation of the primordial mound from which creation sprang, a staircase for the pharaoh's soul to ascend to the stars. This symbolic depth motivated a level of care and precision that went beyond mere technical requirement. The builder was participating in a cosmic story, and every stone had to be laid perfectly to maintain the harmony of that narrative. The separation of cold, hard science from the warm, messy world of myth is a very modern invention. For the ancient engineer, the story was the science, and the science was the story, each giving meaning and endurance to the other in a brilliant synthesis of imagination and intellect. Yet, for all the profound wisdom we can glean from these ancient builders, we must approach this history with clear eyes, resisting the temptation to view the past through a sentimental haze. It is one thing to marvel at the enduring simplicity of a dry stone wall. It is another to imagine applying that same methodology to a 50-story skyscraper. The sheer scale and complexity of the challenges we face in the modern built environment are of a different universe altogether. Consider for a moment the intricate web of life support systems woven into a contemporary high-rise. It is not merely a structure of steel and glass. It is a living organism with a circulatory system of water pipes, a nervous system of electrical wiring, a respiratory system for climate control, and a digital brain managing everything from security to data flow. Coordinating the installation of these interdependent systems requires a level of precision and foresight that transcends the capabilities of even the most gifted intuitive builder. A single misplaced conduit could disrupt the entire network, and resolving such a conflict on the fly would be catastrophically expensive and dangerous. This is where modern tools like Building Information Modeling, or BIM, become not just helpful but absolutely essential. BIM is essentially a dynamic, three-dimensional digital blueprint that contains every single piece of information about a building, from the chemical composition of the concrete to the maintenance schedule for the air handlers. It allows architects, structural engineers, mechanical contractors, and electricians to collaborate in a virtual space, identifying and resolving conflicts between systems long before a single shovel hits the ground. This digital pre-visualization is the modern equivalent of the ancient practice of using the rising structure as its own blueprint, but it operates in a risk-free environment where mistakes carry no physical consequence. The ancient approach, for all its brilliance, had inherent scalability limits. It was perfectly suited for projects where the primary materials were stone, wood, and earth, and where the workforce shared a common cultural and technical language. But it could not have conceived of, let alone managed, the orchestration of thousands of specialized tradespeople from dozens of different disciplines, all working on a compressed timeline. The lesson here is not to dismiss our ancestors' methods as primitive, nor is it to abandon our own advanced tools as soulless and overly abstract. The true insight is one of synthesis. The power of modern engineering lies in its ability to manage breathtaking complexity and ensure safety on a massive scale. The wisdom of ancient practice lies in its deep respect for materials, its flexibility in the face of the unexpected, and its cultivation of human intuition. The challenge for today's architects and engineers is to fuse these two worlds. We can use BIM to perfectly coordinate the skeleton of a building while also creating spaces for the builder's tacit knowledge to shine, perhaps by involving master craftsmen in the design phase to advise on material selection and assembly details. We can specify standardized components for efficiency while also allowing for custom, hand-finished elements that give a building its unique character. We can plan with meticulous detail while also designing structures that are adaptable, that can evolve over time to meet changing needs, much like the ancient cathedrals that were modified and added to across centuries. The goal is not a nostalgic return to a blueprint-less past, but a future where the cold precision of the digital plan is warmed by the ancient dialogue between the human hand and the material world, creating buildings that are not only smart and efficient but also humane, resilient, and deeply connected to their place. So where does this leave us? With a choice that is not really a choice at all. The goal for the future is not to tear down our computer-aided drafting studios and return to the quarry with a hammer and chisel. Nor is it to continue down a path of pure digital abstraction, where designs are so disconnected from physical reality that they become brittle and impersonal. The most promising path forward is one of synthesis, a deliberate and thoughtful integration of ancient wisdom with modern practice. Imagine an architectural firm where the very first meeting for a new project doesn't just include the partners and the lead designer, but also a senior site manager with 40 years of experience and a hands-on materials specialist. These are the people who understand that the beautiful, dramatic cantilever that looks so stunning in the rendering might be a nightmare to waterproof in a specific climate, or that the chosen stone, while aesthetically perfect, might be notoriously difficult to cut with the necessary precision. By bringing this on-the-ground, tacit knowledge into the conversation at the very beginning, we inject a dose of hard-won reality into the design process, catching potential problems when they are still easy and inexpensive to fix. This collaboration transforms the blueprint from a rigid, top-down command into a living document, a shared reference point that benefits from the collective intelligence of everyone involved, from the visionary architect to the practical builder. This is the blueprint as a guide, not as an unchangeable gospel. We can also reintroduce the ancient principle of learning by doing at a scale our ancestors could never have imagined. Before committing to a multi-million-dollar construction project, why not build a full-scale mock-up of a critical section? This isn't a small model. It's a life-sized fragment of the building, constructed with the actual materials and intended methods. The design team, the engineers, and the future occupants can then walk through it, touch it, and experience it. They can feel how the light falls at different times of day, test the acoustics, and identify unforeseen issues with spatial flow or ergonomics. This tangible, kinesthetic feedback is invaluable. It re-engages the senses in the design process, allowing for adjustments based on real human experience rather than abstract predictions. It's a modern application of the ancient idea of using the construction itself as a form of research and development, a low-risk environment for iteration and improvement before the final plans are set in stone, or rather, in digital concrete. This hybrid approach also calls for a renewed focus on materiality and local context as primary drivers of design, not as afterthoughts to be considered once the form is already decided. Instead of starting with a shape and then searching the world for materials to clothe it, what if we started with the materials available in the region? A project in the Pacific Northwest might begin with a deep study of its sustainably managed forests, leading to a design that celebrates the warmth and strength of timber. A building in the Southwest might draw inspiration from the thermal mass and earthy colors of local adobe. This doesn't mean rejecting global materials outright, but it does mean privileging local resources, which reduces transportation emissions, supports regional economies, and ensures the building is inherently suited to its environment. The design emerges from a dialogue with the place, much like an ancient Greek temple was a direct expression of the marble from Mount Pentelicus. This philosophy naturally leads to greater sustainability and a deeper sense of belonging. The ultimate synthesis lies in our attitude toward the tools themselves. Our powerful digital modeling software should be used not to eliminate uncertainty, but to master it. We can run thousands of simulations to understand how a structure will perform under extreme weather events or seismic activity, a capability that provides an incredible layer of safety that ancient builders could only dream of. But we should then use that knowledge to design structures that are not just strong, but also adaptable and resilient buildings that can breathe, that can be easily modified over time, and that use resources with the same efficient intelligence as a dry stone wall. The digital blueprint becomes the skeleton, ensuring structural integrity, while the ancient principles of flexibility, material dialogue, and human-centric design provide the soul. This balanced approach doesn't force us to choose between the past and the future. It allows us to build with the full toolbox of human ingenuity, combining the analytical power of the modern mind with the timeless wisdom of the hand. The result would be a built environment that is not only safer and more efficient but also more beautiful, more humane, and far more likely to endure. So what is the ultimate legacy of these master builders from the distant past? It is not merely a collection of stunning monuments that defy time. It is a radical redefinition of what mastery itself truly means. We have been taught to equate expertise with exhaustive planning, with the flawless execution of a predetermined design. But the world's first engineers show us that the highest form of skill is not about controlling every variable in advance. True mastery lies in the wisdom of the process itself, in the cultivated ability to listen, to adapt, and to respond with intelligence to the unpredictable flow of reality. Theirs was a world built on deep, continuous dialogue. It was a conversation with the very grain of the stone, a listening ear turned to the whispers of the wood. It was a conversation conducted through the body, where the hands became finely tuned instruments for measuring balance and stress, and the muscles remembered the feel of a perfect fit. And perhaps most importantly, it was a conversation within the community, a shared endeavor where knowledge flowed freely between master and apprentice, where problems were solved collectively, and where the intelligence of the many was woven into the fabric of the whole. They did not build enduring marvels in spite of their lack of blueprints. They built better because of their methods, the harmony we sense in their structures, the way a Gothic cathedral seems to soar with a life of its own, the way an Inca wall settles into the earth as if it grew there, is a direct result of this responsive, collaborative approach. The durability that has allowed these creations to stand for millennia is not an accident. It is the natural outcome of a design philosophy that evolved in partnership with the materials and the landscape, rather than imposing a rigid, external idea upon them. As we surge forward into an age dominated by digital abstraction, where we can model entire cities inside computers before a single foundation is poured, we stand at a critical crossroads. The power we wield is unprecedented, but it carries a profound risk, the risk of losing touch with the tangible world. The lesson from antiquity is not to abandon our powerful new tools, but to enrich them with ancient wisdom. It is a call to remember the value of the knowledge that resides in our very muscles, the tacit understanding that comes only from touching, lifting, and shaping. It is an invitation to see our creations not as finished products to be executed from a static plan, but as living collaborations that can grow and adapt over time. The greatest blueprint for the future, then, may not be a set of perfect lines on a screen. It may be something far more resilient and human, the adaptable, intuitive spirit of the builder. It is the courage to begin with a clear intention but without a fixed destination, to trust in the wisdom of the hands, and to engage in a respectful dialogue with the world we are shaping. Let this exploration be a call to build with more wisdom and less ink, to create a future that is not only technologically advanced but also deeply humane, sustainable, and wondrously alive. What do you think? After this journey through the minds of ancient engineers, could we truly set aside our detailed plans and build a modern masterpiece using only their principles of intuition, material dialogue, and collective wisdom? It's a thrilling and perhaps daunting thought experiment. Perhaps the answer isn't a simple yes or no, but a challenge to integrate their profound insights into our own world. I am genuinely curious to hear your perspective. Have you encountered examples of this ancient wisdom in modern design? Maybe you've seen a building that uses local stone in a particularly clever way, or you work in a field like software development that has embraced agile, iterative methods that feel remarkably similar to the responsive building sites of the past. Share your stories and observations in the comments below. Let's learn from each other and continue this fascinating conversation. If this rethinking of engineering history has sparked your curiosity, if it made you see the world of design and construction in a new light, then please do show your support by liking this video. It truly helps this channel grow. And for more deep dives into the hidden mysteries of our past, the stories that challenge our modern assumptions, be sure to subscribe and hit that notification bell. Together, we can keep uncovering the lost secrets of the masters who, with incredible skill and wisdom, built not just for their time but for eternity. Thank you for